You ever look at a massive skyscraper or one of those crazy winding bridges and just wonder, how in the world does that work? How does something that starts as this soupy gray sludge become strong enough to basically touch the clouds? Well, today we're diving deep into the hidden science of concrete, and it all boils down to one single massive paradox. I mean, think about it. The entire world of modern architecture, everything we build, relies on answering this one question. We need a material that can pour into any mold, any shape we can dream up, but then harden into a foundation that's, as strong as rock. It sounds like it shouldn't be possible, right?
Well, the secret isn't just about mixing rocks and sand. The real magic, the thing that unlocks all this potential, is this incredibly cool and delicate chemical dance happening at a microscopic level inside the mix. It's like a perfectly choreographed performance.
All right, so that brings us to our first big idea, what I like to call the concrete conundrum. This is the fundamental battle that engineers have been wrestling with for decades. It's this constant tug of war between strength and, well, flow. Here's the deal, and it seems pretty simple at first. On the one hand, if you add more water, your concrete flows like a dream. It's easy to pour, easy to work with. The problem? When all that extra water evaporates, it leaves behind tiny voids, tiny holes, making the whole structure weaker. On the other hand, use less water, and you get incredibly strong concrete that's so thick and stiff you can barely get it to move. It's the classic trade-off. So, how do you get the best of both worlds? Well, you call in the heroes of our story, super plasticizers. These things are just incredible. They're chemical admixtures that basically act like a super lubricant for the cement particles. They let the mix flow as if it's full of water, even when it's not. They completely solve that strength versus flow problem. But it's not as simple as just dumping some in. Different cements and different chemicals can react in some, well, pretty wild ways. And this is where the real detective work of concrete science begins, running tests to find that perfect, compatible combination. And that is the million-dollar question, isn't it? You can have the best cement in the world and the most advanced superplasticizer, but if they don't play nice together, your project is in some serious trouble. So how do you find out if they're a good match before you pour thousands of tons of the stuff? Well, you start with a tool that's surprisingly simple, almost elegant, the marsh cone. It's a fundamental quality control test. You just mix up a little paste with your cement, water, and the chemical you're testing. You pour it into the cone, and you time how long it takes to flow out the bottom. So simple, but it tells you so much. Now, the real genius of this test is that you do it twice. Once right after you mix the paste, and then again an hour later. If you have a good, compatible match, the flow time curves pretty much lie right on top of each other. But a bad match? Uh-oh, those curves start to pull apart, which tells you the paste is getting thicker and harder to work with over time, and that is a huge red flag. And the marsh cone isn't the only tool in the toolbox. Engineers also use another really clever test called the mini slump test. It's exactly what it sounds like, a tiny version of the big slump cone you see on job sites. You fill it with that same paste, lift the cone straight up, and just measure how much the paste spreads out. And this brings us to a kind of magic number. For really good, flowable, self-compacting concrete, the kind you want for complex jobs, you're shooting for a spread between 160 and 180 millimeters. It's another simple check that tells you if your chemical dose is actually giving you the flow you'll need in the real world. Okay, so not all superplasticizers are created equal. Not even close. In fact, it's best to think of them as a cast of characters, a family of chemicals with 3 distinct generations, and each one has its own unique personality and its own set of powers. First up, we've got the first generation, lignosulfonate. We'll call it the original. Then came the second generation, SNF, which was the workhorse of the industry for a really long time. And finally, the modern marvel, the third generation PCE, which is truly the high performer that has changed the game. But every hero has their weakness. The original, lignosulfonate, can really slow down how long it takes for the concrete to set, which is a big problem. The workhorse, SNF, is pretty solid, but it just hits a wall in those really high-performance, low-water mixes. And the high performer, PCE, well, it's by far the most effective, but it does have a higher price tag up front, though that often pays for itself later with less labor and faster construction. So, talk is cheap. Let's see how these different characters actually perform when we put them under pressure. This is where the lab data really paints a crystal clear picture of who comes out on top. And wow, the difference here is, it's just dramatic. We're looking at slump retention, Basically, how workable the concrete still is after an hour. The PCE mix is still perfectly usable, holding on to 60 to 80 millimeters of slump. Now look at SNF and lignosulfonate. They've pretty much turned back into a stiff, useless pile. It's not even a competition.
And hey, don't just take my word for it. The research is totally unambiguous. It puts it as plainly as possible. Slump retention is also better with PCE-based admixtures. When you're on a job site and the clock is ticking, that's not just a small detail. That is everything.
But wait, it gets even trickier, because check out what happens when the temperature changes. To get the exact same amount of flow, you need nearly 4 times more superplasticizer on a hot 45 degrees Celsius day than you do on a cold 6-degree day. Your entire mix design has to constantly adapt. It's wild.
And this brings us to the final and maybe the most critical piece of this whole puzzle, the huge gap between the clean, perfect, controlled world of the science lab and the messy, chaotic reality of an actual construction site. Because you can do all the tests, you can pick the perfect chemical, you can design a flawless mix on paper. But when that concrete truck gets to the job site, the whole thing can still fall apart. And one of the most common reasons why is something you would probably never guess. It's actually pretty shocking. 30 seconds. That's it. That's how long some batches of concrete are actually mixed on site. 30 seconds. That is dangerously short. A good mix needs at least 5 minutes. And for the really advanced, ultra-high performance stuff, you need 30 to 40 minutes for the chemicals to even disperse and do their job properly. 30 seconds is an absolute recipe for disaster.
So what's the big takeaway from all this? First, making great concrete isn't like following a simple recipe. It's a dynamic science. Second, choosing the right chemical for the specific job and the specific conditions is absolutely critical. Third, you have to test, and test again. You have to adapt. And finally, you can never, ever forget that real-world things like the temperature outside and the actual mixing time can completely destroy even the most perfect lab design. It's just an incredible hidden science that allows us to build the amazing world we live in, and it really makes you wonder, doesn't it? If this is the chemistry building our world today, what kind of new science is going to build the world of tomorrow?